Thank you for joining us this morning for our webinar on J1939. It's roughly about 20 minutes, and as usual, if you have any questions, you can put them into your questions panel and we'll get to them at the end. So we'll get started.
Welcome to today's tutorial. Let's get started. Let's take a look at our agenda. Today we'll discuss what J1939 is. We'll go through J1939 messaging and its configuration in Seascape. We'll discuss decoding J1939 data. There will be demonstrations throughout, and as always, we'll finish with a live Q&A session. So what is SAE J1939? It's a higher level protocol for communications and diagnostics among vehicle components. It uses CAN as its physical layer, so it's quite robust. It was developed by the Society of Automotive Engineers, now known as SAE International. J1939 is largely responsible for hundreds of millions of CAN chips and devices sold each year. J1939 is used today in many industries, including automotive, agriculture, construction, fire and rescue, ships, power generation, and pumping. It is based on the 7-layer OSI model, with CAN operating the lower 2 layers. Different J1939 specifications define different elements of the model. Today we'll focus on the application layer, which is where the data we can use to interface our control equipment is found. J1939 is a true peer-to-peer and broadcast protocol. With peer-to-peer type messaging, you can have one-to-one type communications. With broadcast communications, it's one-to-many. Many broadcast messages are sent to the network unsolicited on a periodic basis. J1939 messages use a 29-bit CAN identifier with 8 bytes of data. Buried within that identifier, there are 18 bits of PGN, which stands for Parameter Group Number. The data for each PGN contains parameters called Suspect Parameter Numbers, or SPNs. SPNs are the important data that's exchanged over the network. Most OCS applications for J1939 involve acquiring data from the engine or vehicle component. Most of the important data is broadcast automatically by the vehicle component. The Horner OCS is also able to transmit data and request data that isn't automatically broadcast. Today, we will be discussing receiving and interpreting broadcast data. Now we'll go through the overall process of J1939 applications with the OCS. The first step is, if possible, to acquire a copy of the PGN and SPN list from the equipment manufacturer. The second step is to find the SPNs you are looking for within the list of available PGNs. The third step is to configure the OCS to receive the PGNs containing the important data. And the last step is to write logic to extract each SPN and scale it to the appropriate engineering units. Now we'll discuss which Horner OCS controllers support J1939. Our single CAN OCS models support J1939. However, it is optional, so you need to order a J1939 firmware extension from Horner. You will also not be able to use it simultaneously with another protocol, such as Cscan or CAN Open. These controllers include our RCC controllers, except for the RCC 6512, the XLE, XLT, X5, XL4, EXL6, and EXLW. For our dual CAN models, J1939 is standard and selectable during configuration. These are the XL7, EXL10, and the XL Plus 15-inch model. Now we'll discuss configuring J1939 in Seascape. You start in the Hardware Configuration tab and select J1939 from the drop-down list. Once you've selected it, press the Config button next to that port. Then you'll select the default message database, which is manual definition. You'll configure the network baud rate. You can select either 250K or 500K. Now you'll select your control structure variable. If you're using register-based logic, you'll configure the starting register for controlling status. If you're using variable-based logic, you'll assign a word type variable that's dimensioned as an array. You can use standard PGN mode, which supports 15 transmit and 15 receive PGNs. You can also use extended PGN mode, which supports 32 transmit and 32 receive PGNs. The control structure variable performs several functions. Each function is performed by one or more words of information, and they're all listed here. The first variable can be used to start J1939 communications with the OCS. You can use variables to trigger a remote message request or transmit message triggers. You have a status variable available and another variable to indicate received messages. There are also variables for receiving and transmitting table counts. The status register has many error messages, which are displayed here. A whole variety of diagnostics can be used with this status variable. Now it's time to configure the OCS to receive PGNs. Every PGN requires 6 words of variable space to be allocated to it, with a maximum of 192 words. If you're using register-based logic, you just need to configure the starting register and the consecutive registers are allocated for receiving PGNs. If you're using variable-based logic, you need to assign a word type variable as an array with a dimension of 192. Next, start adding in individual PGNs to be received. You can configure up to 32 of these. We've got the details on screen of all the different fields you can configure for each individual PGN. You need to enter the PGN number, which is the identifier. You can set the priority between 0 and 7, with 0 being the highest and 7 being the lowest. You can configure the broadcasting node or source address. The default of 0 works a lot of the time. You can name the PGN whatever you like and set the number of bytes. You can configure whether it's a broadcast message or a message that has to be requested. If you're requesting it, you have to fill in the frequency in number of milliseconds. You have to allocate the data that's receiving through a variable, either 4 consecutive registers or a word array of size 4. The process for configuring transmit PGNs is almost identical. You need to allocate either 192 consecutive registers, or in the case of variable-based ladder, a word-based array of 192 elements. Every time you want to add a new transmit PGN configuration, you hit the Add button. Most of the fields for the transmit PGN are the same as the receive PGN. What's the PGN number? Where are you going to name it? What priority does it have? What's the node number of the OCS? And lastly, what variable are you assigning it to? So that was configuration of J1939 in Seascape. Now let's demonstrate this in Seascape. I'm in Seascape, and I'm going to create a new program to show you how to configure J1939. I'm using register-based ladder, but variable-based is very similar. I've started a new project, and I'll start by going directly to the hardware configuration. Now I'll select the controller that I'm going to use in the application. I've got an XL7, which can support J1939 on port 2. I'll select J1939 from this drop down here and hit the config button. We'll start at the network level. We're going to use the default message database, and we'll leave our baud rate at 250K. Next, we have to decide whether to enable extended mode with up to 32 PGNs for transmit and receive, or select standard mode, which has 15 for both. We'll choose extended mode. I'll allocate register 1 here, and down here it'll show what each of the 10 words in my control structure are going to be used for. So that's all the configuration I need to do on the network level. Now I have to prepare the OCS to receive and transmit PGNs. So under received PGNs, this is where I have to allocate 192 words of variable space for receiving PGNs. I'm just going to allocate register 1001 here, which means that register 1001 through 1192 will be allocated towards receiving PGNs. I've got many options down here that I will leave as default. So the configuration is complete for receive PGNs. Now I'll configure transmit PGNs. It's very similar. I need to allocate 192 words with a variable space for transmitting PGN data. So that's all there is for the basic configuration of the OCS for J1939. Let's go back to our slides. Now let's discuss what happens once PGN data starts coming in. Once the PGN data comes in, it's usually 8 bytes. Often this data will consist of several SPN data values packed into the 8 bytes, so you'll need to isolate the specific SPNs that you are interested in. There are some logic instructions that are very useful for this. Let's say this is 2 bytes out of the 8 bytes that came in from the PGN. Let's say the specific SPN data we're interested in is the 8 bits of data in yellow. We want to keep that information and get rid of the extra data that was transmitted. To do that, we use a function called a bitwise AND, which goes bit by bit looking at this in binary. We will replace the bits we don't want with zeros to return what we want. In this particular case, the bits we want in the center are equivalent to 4080 in base 10 binary. So when we do the AND function in Seascape, we'll take the data in that word that we've received in and add 4080. And then the result is what you see below in the center of the slide. The data that we have at the bottom is in the center, so it is not going to be interpreted properly unless we align it with the right side of the word. So how can we do that? We can use divide and multiply commands to shift the data up or down. If we need to shift data up, we can use the multiply function. If we need to shift data down, we can use the divide function. If we want to shift those 8 bits over to the right by 4 places, we need to divide by 16, as it is 2 to the power of 4. So that was the bitwise AND function, and the multiply and divide functions. Now we'll show some demonstrations of real-world applications. For this demo, we'll talk about engine coolant temperature, which is highlighted in yellow and is SPN number 110. It's part of PGN 65262, which has multiple SPNs. We're interested in the first byte, so we're going to remove the data we don't want in the other byte. And then this data will be adjusted to the appropriate temperature range. We'll demonstrate this in Seascape now. I'm in Seascape with a pre-configured program for dealing with some PGNs. Let's go in and start at the configuration level. I'm going to J1939 and I'll go to the configuration. Let's take a look at how we configured this. At the network level, we used mostly default settings. Here is our control structure variable, which is a word variable with a dimension of 10, so it has 16 consecutive words. Here are the details for each member of the arrays function. More detail on this is available in the help file. From a receive PGN standpoint, we have allocated 192 words using a word type variable array with 192 members. The first member is listed here, and I named it J1939 underscore PGN underscore RX. The first member is sub-0 and it goes up to sub 191. On the transmit side of things, I've assigned another variable to allocate 192 words of variable space for transmitting PGNs. Now let's look at the details of the PGNs that we received. And we're going to start with our engine temperature. The PGN number is 65262. I typed in engine temperature 1 as the description. Priority is not important because we're receiving the data in, and that is handled by the transmitting node. It is coming from node address 0. Destination address is not important because this is a broadcast message. The data size is 8 bytes, and I've assigned it to the variable array that I've created. Monitor mode is selected, and it's not a message that I have to request. So that's all the configuration required to configure the first receive PGN. Now we'll look at what this looks like in my XL7. I have my XL7 here running the program, and we're looking at PGN 65262. I've lined up the data that we're receiving in on screen. In J1939, when you receive in a PGN, it'll contain multiple SPN parameters. Any SPN that's not supported will report a value of FF, which happens a lot. From looking at the first variable word, the first 2 bits are FF, and the following bits are counting down. The data that we're after is in the lower half of the first register, which is those last 2 bits. If we're converting that to a decimal value that we can use in our program, we need to strip off the first 2 bits, which we aren't using, which are in the upper byte of FF. So to do that in our program, we're going to take our data in that first register and AND it with 00FF, which is all 1s in the lower half to keep all that data, and all 0s in the upper half to get rid of all that data. So our end result after we do that is 0069, or whatever you can see here on screen. Then the last step is to scale it to temperature, which in this case just needs an offset of -40 to get our value. The value we're after here is the coolant temperature, and here's how it came in. Here's the processing that we did on it, and now I will take a look at the logic that's used to process that PGN. We've got an AND block where we're adding the first word of data that came in with 00FF hex, which is 255. The result of that goes into another variable, which we're calling coolant temperature raw. The reason it's raw is because it has not had an offset applied to it yet. The next function block adds -40, which is the offset, and it creates our coolant temperature variable. So that's all there was to this example. Let's go back to our slides now and show you our next example. Now we'll look at the next PGN that we want to deal with. With this one, we're interested in engine speed in RPM, which is highlighted on screen. Its SPN is 190, and it's all part of PGN 61444. The name of the PGN is Electronic Engine Controller 1. Now we'll showcase this in Seascape. Let's take a look at the configuration of this receive PGN. We'll go back to hardware configuration and back into J1939 configuration. So here's 61444, which is the PGN that we want. Here's the description we put in. Priority is not important, and we're receiving the data from source address 0. Destination address is not important in this case either. We're in monitor mode, and we've assigned the forward variable that I named PGN 61444. That's where the data is coming in. Let's have a look at this program in the XL7. So now I'm looking at my controller. Here is the PGN where we can extract our engine RPM. Just like last time, I've isolated the data coming in from that PGN over here. So here are the 8 bytes coming into those 4 word type variables. But this time, the data we're after is 16 bits long. It's made up of 2 different bytes, which are located in 2 different words. The least significant piece of data is here, and the most significant piece of data is here. So we've got a little more work to do with this one, but the process is ultimately the same. We start by isolating the bytes that we care about. So in this variable, we're going to end it with FF00 to keep everything on the left and to get rid of everything on the right. We'll do the same thing down here. We'll mask off the top by ending it with 00FF, and then we have our isolated data. Now, the problem we have is this is supposed to be my least significant byte, but it's my most significant byte and in the wrong location. So I need to shift this bit down and this bit up. I'll use my divide function to shift this bit down and my multiply function to shift this other bit up. So now we've got the information in two different words, and we'll use the add function to put them together. Our result is in this variable over here. This variable has not been scaled to RPM yet. We need 0.125 or 1/8 RPM per bit. So we need to take that value that we've created and divide by 8. So our final value is here in the bottom right in decimal. So that wraps up today's demonstrations. Thank you for attending today's tutorial. The Q&A session will begin shortly.
Okay, so that was that. I'll just see if we have any questions in. Not seeing anything at the moment. So we shall go back to my screen. Which hopefully you can all see now. So we do have using structures with variable based next week into bootloader updates the following week and can open networking on the 16th. We are putting together a list for webinars starting in January. So we shall have that up soon enough. And as always, if you have anything you would like to see and hasn't been already shown in a previous webinar, do let us know and we'll try and incorporate that. And you have all the past ones there if you do need to run back through them. Yeah, so I think that covers everything for today. Thank you for joining us and hope to see you again next week.